we were talking about the Beurling transform. And we'd shown the following thing. If we take the L2 norm of the Beurling transform applied to any function f, which is the infinity of compact support, then it is just the same as the L2 norm of the function f. The L2 norm of the function f, like this. And that's where we were. And I asked you to think about and tell me why this allows us to define the Beurling transform on the entire space of L2 functions from complex plane to the complex plane. So, suggestions on this. And therefore it's complete, so I'll have a Cauchy sequence from this inequality right here. Good, yeah. So given, exactly to say, any f belonging to L2, complex plane to the complex plane, by density, can take compactly supported sequence, complex plane to the complex plane, such that in the L2 norm, I'm just going to write L2, this tends to 0, as k tends to infinity. Yeah? So, if we consider this sequence, it's going to form a Cauchy sequence. In L2, because we just applied inequality. Let's call this k and f of km, like this. L2 is equal to this thing, because it's a linear mapping, linear transform, like this. So there exists a unique limit inside this Banach space. This is a Cauchy sequence inside L2, so there exists limit in L2 complex plane, the complex plane. And we define this limit of this Cauchy sequence to be the Hilbert transform on an arbitrary f. Like this. Cool. And this is now completely well defined. It's a uniquely defined linear operator. And we know that in the specific case of when we have a continuous smooth function of compact support, then we actually have this representation. So now defined on the whole of L2. And if f is smooth, then we actually have the representation that we know, that f of s point z is minus 1 over pi, the limit as epsilon goes to 0. Our consistency, let's do the double integral. Complex plane, take away the ball of radius epsilon around z of f of zeta, zeta minus z squared dz, like this. Yeah? So this, at this stage, we know this limit exists. It makes sense so long as f is actually smooth. We don't actually know this representation for an arbitrary f in L2 at this point. You know? It turns out to be true, but that's an additional thing that requires proof. Yeah. So for an arbitrary function in L2, we just know this thing as the limit of this sequence of Beurling transforms applied to this sequence of functions. You know? You know? But that's good enough for our purpose, because the main thing we're interested in is these various derivative inequalities that we've proved about the Beurling transform, specifically that the Beurling transform sends the anti-conformal part of the gradient to the conformal part of the gradient. Yeah? So we know that S of df by dz bar is equal to df by dz, and again this is just for smooth so far. And this came from our various identities that we proved that if we take the conformal part of the gradient of the Beurling transform, we end up with the Cauchy transform. And when we do the Cauchy transform and we take the anti-conformal part of the gradient, we end up with the identity. Right? These two guys allowed us to conclude this. Yeah? Cool. Now this is the thing we particularly want, but now we want it for arbitrary functions. We want it for arbitrary functions. And we also know that derivatives can be passed through in the smooth case, so we can write this as d by dz bar of s of f, like this. That's another way to write the identity. Yeah? And what we're going to do is we're going to try and, well, we are going to succeed to actually have this identity in the form of weak derivatives for arbitrary functions in L2. Okay? So if we have a function L2, this no longer makes sense, right? But this thing does make sense as a weak derivative, and this thing does make sense as a weak derivative. Yeah? And that'll be our goal, because ultimately to use the Beurling transform to prove the existence of solutions of the Beltrami equation, we need to apply it to functions that are not smooth, because that's the statement of this solution to the Beltrami equation, that for an arbitrary measurable coefficient, which is called norm strictly less than 1, we can solve the Beurling equation, right? And that means dealing with coefficients that are not smooth, and the machinery of that is going to be of proving that will be using the Beurling transform, and so we need to get out of smooth world and prove these identities in arbitrary L2 world. And that's where we're going to with the next section. Now we're going to start talking about an operator that's slightly different than the Cauchy transform I talked about before, but it has all the nice properties that we want. So we're going to find this operator P of f of z to be minus 1 over pi, the double integral over complex plane of f of zeta, zeta minus z, minus f of zeta over z zeta. Now, we can write this just like this. We can break up the integral into these two separate parts. Over pi, double integral like this, zeta minus z dz, I can write it as plus 1 over pi, double integral over the complex plane like this. And this part right here is just the Cauchy transform we defined before. This is exactly the Cauchy transform. And this thing is some constant that depends just on f. Right? So this doesn't depend on z, this integral. Right? The z is in this thing right here. So once we carry out this integral, then it is just some number. It's a fixed number. It's independent of z. Yeah? So it's just a constant depending on f. So we're going to write this. Actually, let's write this better. So this is the Cauchy transform applied at the point z to the function f, evaluated at the point z, and then plus some particular constant, and we're just going to give it a name. Let's call it this script O of f. Okay, which again doesn't depend on z. It's just a fixed constant once we choose f. No? We don't have to talk about the limits existing around the singularity, because as we discussed before, this is an integrable kernel. We know straight away that we can take the limit as epsilon goes to 0, and there's nothing going to happen. The little ball of radius epsilon around z, the integral of this expression goes down to 0, so for sure this limit exists. And the same is true for here, so no principal value necessary. This is well defined just as it is. No? Cool. So this operator P satisfies the cool stuff that we know for the Cauchy transform, because what we know that if we do the Cauchy transform and we take the derivative, once again, this is the conformal part of the derivative, this just gives us the Beurling transform. If we apply this to P, then the same thing is true, because this constant is just going to vanish when we differentiate with respect to z. Yeah, maybe I should write that more explicitly. No, I mean, that should be good enough, right? So that's just f of s. So the P of f conformal part of the gradient is again the Beurling transform. Yeah? And the other identity we know is that when we take the anti-conformal part of the gradient of f like this, then we just get back to f. And so this implies the same thing is true of P. Yeah? So long as we take the derivative on the outside this time. Yeah? Cool. So what's the advantage of this thing? Well, the advantage is that we can show that this guy is bounded as an operator from LP for P bigger than 2 into, it's actually going to be into the whole of continuous functions. So theorem. First step is to show this. So for f, which is then what we have that P of f evaluated at z is going to be less than some absolute constant times the L2 norm or LP norm of f, and then z to the 1 minus 2 over p, like this. And then from this, we're going to show, as I said, I mean, it's a non-trivial step. We're going to see this allows us to conclude that actually p is mapping into the whole of continuous functions with whole exponent 1 over 2, 1 minus 2 over p. That's what we're going to conclude from this. But this is what we're going to start with. So I'm going to do this calculation. It's a little bit lengthy. So if you remember how this went before, we had no problem around the singularities, around the singularity around z, right, for p bigger than 2. That allowed us to have enough integrability to show that that singularity didn't prevent us having a finite controllable integral. We had a problem as we go towards infinity. Well, here we have two singularities, the singularity around z and the singularity around 0, but the p bigger than 2 still allows us to conclude that this is finite. And the problem which I had when I took the zeta going out towards infinity is now much less of a problem, because we have these two things here. We have this thing minus this thing. And that allows us, so we'll make a common denominator, and then you'll see that this thing is now blowing down as we go towards infinity fast enough to allow us to conclude the thing is finite. So if you remember that argument and you've done some kind of estimates with LP things and alternate inequality, then what I'm about to do will seem kind of natural. Otherwise, you'll just see it's a calculation, and it'll follow, as I say. We're going to consider what happens when we consider locally around the singularities and show that that's not a problem. And then we're going to see what happens when it happens globally. Okay, so let's do the calculation. Okay, so let's draw a picture. So we have two singularities around z and around 0. So suppose z is here and 0 is here. So we're going to first consider balls that are just around the singularities and that are separate. So, for example, let r equal mod z over 4. Why not? And then we're just going to consider the integral around balls of radius r around the singularities and see what happens. So I'm just going to do this guy, and this guy is totally analogous. So if we do the double integral around the ball of radius epsilon around z of f of zeta minus z dz, then this will be fine because we're going to put the integral inside this thing. So we're going to do integral epsilon radius z, absolute value of f of zeta, zeta minus z, like this. dz, we're going to apply, let's do the double integral of consistency. We are going to apply Holder's inequality, so it's p integral for p bigger than 2. So then this is going to be f less than f of LP. So we're just, Holder's just going to give us this LP on this ball, but we're not going to care because everything's going to be bounded by the LP norm. So we're just going to say this is bounded by the entire LP norm of f. And then we're going to have the double integral, the ball of radius epsilon around z of 1 over zeta minus z to the q, where q is the Holder exponent, 1 over q. So 1 over p plus 1 over q is equal to 1. Right? So then this is the guy we want to check is finite. Let's call this thing star. And star. Let's do that calculation. So it's the integral from, I'm going to use the Cauchy formula, so 0 to this, integral around the boundary of the ball of, say, radius s around z. We can, okay, it doesn't make any difference. Let's just do it around z. So then the ball of radius s around z, this function is just constant, and it's equal to 1 over s to the q. That's right, dh1 of w. So that's an integral, and this is the out integral. This is just the Cauchy formula. We've used this before. And then what's this? 1 over q on the outside. And then integral from 0 to epsilon. And then this is going to be, so we're going to have this 2 pi s from this. So we're going to have 2 pi s of 1 minus q, like this. And then it's just ds. So I, 1 over q, don't care about the constants, so I'm just going to say less than equal to and not have to pay attention to it, like this. And then this thing is 0 to epsilon, s to the 2 minus q over 2 minus q, like this, and put a constant here. And then we are totally happy because since p is bigger than 2, 1 over q, start again, since p is bigger than 2, q is less than 2, and therefore this is a positive exponent here on the top, right? So then this is less than c epsilon to the 2 minus q, yeah? Which is some small quantity, yeah? So when we have integrability for p bigger than 2, then this singularity around z is not a problem, and the same thing will happen around here for 0. Yeah? And everything will be bounded, this will be bounded by the LP norm of this guy right here. And actually, we're not doing this a ball around epsilon, we're doing this a ball of, let me just call epsilon here, radius r. And I think I actually want to incorporate that because we have this exponent right here. And so then this is actually less than constant times mod z to the 2 minus q. And if we mess around with the Holder exponents, So 1 over q plus 1 over p is equal to 1. Let's write 1 over q minus 1 equals minus 1 over p. Let's multiply by 2, so 2 over q minus 2 equals minus 2 over p. And therefore, 2 over q minus 1 is equal to 1 minus 2 over p. And that's right. And that's exactly what we have here, right? That's exactly this thing. So this is equal to C of mod Z 1 over 2 over P, as claimed. Yeah, as claimed. Cool. All right, so the part of the integral which is around these singularities at Z and at 0 is going to exactly contribute what we want. It's going to be LP norm of F times Z1 minus 2 over P, exactly as claimed. Okay, so now we consider this integral outside. So we're going to consider this integral complex numbers, and we're going to take away the ball of radius r around 0 and the ball of radius r around epsilon, like this, and our integral is this, f of zeta z minus zeta. So I'm forgetting about the constants for the time being, because constants we don't care about in this calculation. The zeta, right? This is the thing we have to estimate. So let us just get all the way outside the danger area near the singularity. So this is 0, this is z, and the distance between them is r. Or this is like 4r, the way I defined r, right? So then this is less than, let's break this up into the integral around, say, a ball of, let's say, 2 mod z around 0. Take away these guys. And then the same thing, blah, blah, blah. And then everything outside. So then complexly b of, should be minus, thank you, should be minus. Zero like this, and this time I'll write it. Zeta minus z, dz, let's have to put it all together, minus f of zeta over zeta. Zeta. This is 0, and this is z. Okay, so I claim that this guy isn't going to be a problem because what we know. So we know that the kernel out this z minus zeta and this zeta thing, the biggest this thing can possibly be on the bottom in both cases, I'll write that, is when they're as close as possible to the singularity, and as close as they can be to the singularity is just going to be r, right? So then let's call this guy star, right? So the kernel is bounded above by 1 over r in both cases, right? So this is 1 star. So star is less than r to the minus 1, and then we can just take the LP norm of what's inside here, right? So applying holder. So once we take out the once we take out the kernel, then we just have 1 times this function. So let's apply holder to that. So we're going to have this is less than the LQ norm of the constant function LQ on the ball of radius mod 2 mod z around 0. times the LP norm of the function f. Yeah. And then what is this thing? Well, this thing, it'll just be the integral of 1 to the power q, right, over the ball of radius z. So that's just going to give us pi times 2r squared, and then to the root power of 1 over q. Right, so then this is less than equal to r to the minus 1 of pi times 2 mod z squared to the 1 over q, like this, times this, ALP of this guy. And then these things are comparable because this is less than some constant times mod z. So putting all the powers of mod z together, we are going to have mod z of 2 over q minus 1, and I think that's the same exponent we had before, which is the same as 1 over 1 minus 2 over p. Right? I don't want to cross into this. Let's put a constant here. So that's equal to a constant of mod z of 1 over 2 over p. F of LP. So that part is no problem. Yeah, so this part here, which is like this, so it's away from the singularities, but it's in a finite ball of radius comparable to mod z. That part is fine. We can control it. Yeah? Thumbs up if you're with me here. All right, cool. And then the part we have to worry about is this outer part right here, or the final part, which we're going to call star star. That's the part where things went really south when I tried to do this for the Cauchy transform directly. So let's look at this angle. Let's go back to double. But I can't. I need to use both. Good job. I didn't continue with that train of thought. So let's actually put this on the common denominator. F of zeta of 1 over zeta minus z minus 1 over zeta, like this. D zeta. Let's make a common denominator. This is equal to this. I nearly repeated the disaster of the other day. So then common denominator, we have f of zeta. And so then this on the top will be zeta, and then it will be zeta minus z, and then everything over zeta minus z times zeta, right? D zeta, and then the zetas will cancel, and we'll just have positive z on the top here. Positive z on the top, yeah? Cool. And then if we take the absolute value signs of this thing, so I should say that this is absolute value signs of star star, like this. Then let's take the absolute value inside. Let's take z outside. So then this is less than mod z. And then double integral, complex numbers, p2 mod z of 0. And we are going to have absolute value of z. And then absolute value of zeta minus z, zeta, d zeta. Cool. Now, we are going to apply the Cauchy formula. So then this is less than this. Now, the thing I was saying previously is now relevant for this calculation. So as we are outside a ball of radius 2 mod z, then what is this thing looking like? This thing I claim is like some constant of of 1 over mod z, because we're sufficiently far away. So claim. So z is less than a constant times 1 over mod zeta for any zeta belonging to the ball, or belonging to the complex plane outside the ball of radius 2z. Okay, that's my claim. So why is that true? Well, as we go out towards infinity, it's definitely true, right? It's definitely true. Yeah. So whatever constant you want, let's say you want a constant of 2 here, then there exists some radius where if mod z is bigger than that radius, then this is definitely true. Yeah? And inside that radius, then both of these quantities are just bounded. Both of these quantities are just bounded. So there's definitely a constant inside that radius. Yeah? So therefore, there exists a constant. We could explicitly calculate it if we want, but it's not important to us. There exists some constant like this, such that this is true. Yeah? Cool. Like this. So we are going to use that. So then this thing, it's going to be less than, let's put the constant right here. Then this thing is going to be less than double integral of the complex plane of b times mod z around 0 f of zeta over mod zeta squared. And this is what makes us very happy, because now, as we go towards infinity, we have this better decay. So previously, when I had a power of 1, it just didn't work, right? But now it's actually going to work because we have the sufficient decay as we go towards infinity. So now we just apply the Holder inequality. So we have this, and just the LP norm of the function on the entire complex plane. And then this integral. So we're going to do the integral of this thing. I'm going to directly put it into Cauchy formula. So mod z to infinity, integral of the boundary ball of radius s around 0 of around ball of radius s, and this is just 1 over s squared dh1 of w, and then integrating around all the radii ds. And then this is something we just calculate. So this is mod z f dlp. And then this is going to be the integral from 2 mod z to infinity. And in here we're going to have, so I'm going to forget about constants. So there's 2 pi, I just forget about it. So then this integrating around the boundary of the circle just contributes an s. But we have an s we have 1 over s, so we're going to have minus s like this. Q, 1 over q. Yeah, good. Otherwise, things go horribly wrong. So what do we get? So then we're going to get s of the power 1 minus 2q, like this. Yeah, that's what we get. And that will be the good thing, because I'm joining this and then to 1 over q. And then this is mod z f to the LP. And I'm going to do this terrible thing that I keep telling students not to. I'm going to just put infinity into this expression, like this. And then I have 2 minus q over 2 minus q. So yeah, q is still bigger than 1, right? Q is still bigger than 1, right? Q is between 1 and 2. So this is indeed a negative power. So this indeed will not blow up. So this is a finite integral. So yeah. So then this is, let's put this inequality up here. So yeah, let's put this up here. So then this is less than mod Z F LP, and we are going to have just this times, so there's a constant, of course, we're going to have just of this, so this is mod Z to the, so this one is this, but there's a minus sign from this part, so everything's good. So then this is just 2 over 2 minus Q, there we go. Okay, good. So then now we're in good shape because it's constant times the F of LP times we have mod Z over 2 over Q minus 2 plus 1, so it's minus 1, and then that's the exponent we had before, right? So then this is again constant times mod Z of LP of Z of 1 minus 2 over P, like this. Cool. So, I was about to say by straightforward estimates, but I stumbled through this with some difficulty. Nevertheless, by straightforward estimates, just applying a holder step after step after step, then each part is giving us the same bound, which is a constant times Z to the 1 minus 2 over P. Here we have it again for the outer part, and we had that for the inner part. Yeah? So we can control every single part of this and show it's bounded always by this expression, and that's exactly the thing that we claimed in the result. Yeah? Cool. All right, so I am over time. For Monday, a nice little exercise. Try and go from this bound to showing that we actually have Holder continuity of the operator P acting on LP functions, in the sense that P of F of acting on Z1 minus P of F acting on Z2 is less than constant times LP norm of Z1 minus Z2 to this exponent of 1 minus 2 over P, like this. Try and show this. It's a neat little exercise. And that's what we're going to use, because now that we start to have parts of this stuff in LP, we are going to be able to write down our identities in a weak form, and then ultimately be in a position to prove the solution of Beltrami equation, which probably will get done next week. All right, have a great weekend, people. Thank you for your help along this class. See you all on Monday. Bye-bye.